Okay, had some trouble on the audio. Ought to be able to do this part pretty quickly since I practiced it a couple of times. One thing I wanted to note to you about the solar radiation load. Um, we enter the solar radiation load is calculated for a nominal type of glazing, which is single strength, very thin glass, very clear glass, the kind of glass you'd probably might be able to buy from a hardware store, but you'd only use it for like a picture frame. You wouldn't use it in construction. It's too weak. It's too thin. So in construction, the glass will be thicker and it'll have more impurities in it because why not? It's not important. The very clear glass, you'd only buy it like picture frame or solar water heater. So the shading coefficient, that data gave to you in the homework assignment. It's here with the fenestration data. It has a shading coefficient of 0.75. Now notice that normal incidence, this glass has transmittance of about 0.7. The water white glass would have a normal incidence transmittance of about 0.92. It only uh, loses transmittance because of reflection at the two interfaces. Take that 0.92, multiply it by 0.75, and you get about 0.70. So you see that this shading coefficient, it accounts for the extra uh, uh, attenuation compared with the nominal. Okay, so next thing is we'll look at the internal loads. First of all, internal loads for equipment. This probably seems fairly reasonable, about 1 watt per square foot. Multiply that by the office area, not the corridor area, office area, and that gives us the um, uh, nominal load per hour. Now, since the building is only occupied for 10 hours, the majority of the heat will be released in that 10 hours, but some is absorbed into the building materials, and then by the thermal flywheel effect, it's released later. So our first hour of occupancy is the hour that ends in 10 by clock time. But as we looked before, that's hour 8. Hour ends at 8 in solar time. So here are the cooling load factors. Actually, in what you have, you probably have a 1 here, or maybe 1 bogus number to make sure that you're paying attention here. And so that's what it looks like to you. Notice these cooling load factors just account for smearing 10 hours into 24 hours. So it should add up to 10. If I go back to the number that I'd already put, that's 83. And so that's about right for, uh, uh, or that agrees with the table. It's numerically 10 hours. So that's and that's all sensible heat. These other data are just for different arrangements of uh, different hours starting at different times of the day. So that takes care, this column is the only one active here. And so that takes care of the um, equipment load. Notice here we are assuming a type C space, moderate heat capacity, moderate flywheel effect, which to me seems reasonable, particularly for the way we would actually use it in the CLTD method. Next we have people, either from the building owner or at the very least from the standard number of people per space from standard 62. We'll have number of people to be expected in the building. Now to get the loads, now people are going to have sensible and latent loads. So we've seen this kind of data before. Here's the sensible heat and latent heat. We're assuming moderate office work. Why not? Okay. Sensible 250, latent 200. Now, same thing here. People are, a type of equipment that 10 hours of our working in the space will be spread over the 24 hours. The cooling load factor for people is assumed to be the same as it is for equipment. In my simulations and measurements, I can't tell a difference between people and equipment in the heating load. You probably have a 1 here. Make sure check the table and make sure that you get the right amount. Check the sum, huh? Then you'll be sure. Now, the sensible load, uh, when a person's in a building, some of their heat is absorbed by the materials before it gets into the air, and so that's why it has a thermal flywheel effect. The latent, no, we're breathing water vapor directly into the air. So here's the sensible heat load from people smeared over 24 hours, but the latent load comes instantaneously. So it's just there during the 10 hours of occupancy. Lighting is similar, although it has a slightly different, I don't know if it's justified, slightly different cooling load factor. I assume there's 1 watt per square foot. That's a little bit high, but easily, and of course we can easily meet standard 91 with LEDs today. Uh, so for work lighting, 1 watt per square foot. And in addition, we have some security lighting. Now, make sure you have the right conversion factor from watts to BTUs per hour. Have the right area. This is office area only, whereas the security lighting, I assume, for the whole building. Okay, now, so we take the hourly load, multiply it by the appropriate cooling load factor, which is exactly the same one for people. Now for the security lighting, I just put this in here primarily, because there probably would be some, but that's running continuously. So it's already saturated the heat capacity of the building for this kind of, for this energy input. So it's going to be continuous for the whole period. Okay, so that's given us our people and equipment and lighting. Now the outdoor air loads. So we have outdoor air load for ventilation and for infiltration. Let's take a quick look at our modeling for those things. And that's in here. Okay, now infiltration mass flow rate, calculate that using the air change per hour method. So, this gives you something not unreasonable. Now, this could be as little as 0 in a modern building that's kept pressurized. So it'll be probably a fraction of 1. Outdoor air density times the air change per hour times the volume of the building. So this will be in cubic feet. This will be in inverse hour. This will be in pounds mass per cubic feet. So it'll give you pounds mass per hour. So, and then notice for both the outdoor air loads, I showed you how we can split it up into sensible load using the moist specific heat. Oh, I always do that. Moist specific heat. And then that sensible load depends on the temperature. And the latent load depends on the humidity ratio. And I showed you that it's reasonable to assume a constant humidity ratio for a given day. Temperature changes noticeably, right, over the day, but as the same air is heated or cooled. But changing the humidity ratio means changing the whole mass of air. Could happen quickly if a storm moved through, but typically it does not. And then the ventilation is similar. We have the ventilation from our analysis based on standard 62. And once again, so we have that in cubic feet per minute, though. Remember to change that cubic feet per hour. Let's go back to the spreadsheet. And so here we'll calculate the loads for ventilation and the loads for infiltration. Now let's take a look at this calculation. The sensible load depends on the temperature difference. So we need to know the outside temperature. We calculate that by subtracting from the maximum temperature some percent of the temperature range. In this case, 17.1. 0 here, this is the hottest hour. The fifth hour is the coolest hour. We're subtracting 17.1 from 91.5. That's the coolest hour of the day. So we use that temperature difference, or use that temperature in the difference, to calculate the sensible load. The latent load, though, doesn't change because we're assuming the humidity ratio doesn't change. Due to ventilation, calculations are similar, but notice here we assume we're cut back just to the per area ventilation. Maybe you could even cut back lower than that, to the per area ventilation when the building's not occupied, and then add in the extra ventilation when the building is occupied. These loads will be, of course, instantaneous because this is air being mixed directly with the air in the space. So that finishes the internal loads and the outdoor air loads. So that finishes the calculations, and we'll look next at the summary results. And I'll probably post that for you maybe on Sunday or maybe just on Monday after we look at it in class. Okay.